We worked out the 2004 multiple choice problems in class, and the 2008 solutions and what you should know are actually provided kind of in AP format. So I wanted to do just one kind of set of video solutions to this multiple choice section that I gave you yesterday, just to help you study and prepare for the test. So I have it on Haiku or Power School, whatever we're calling it now, which problems you should be able to solve. They're listed on the page, and I'm just going to go ahead and solve all of them now. This is a bit of a longer video, but I hope it's helpful. So in the absence of air friction, an object dropped near the surface of the Earth experiences a constant acceleration of about 9.8 meters per second squared. Now, we've talked about this before, so let's be really clear. This is absolutely not true. That is not the speed. The object falls 9.8 meters during each second. That would imply a constant velocity. It actually turns out these say the same thing. And they both say the same incorrect thing. This is actually false. During the first second, I'll leave you to prove this, but it only falls 4.9 meters during the first second. Now, this would be nice if this were the derivative with respect to the velocity, but it's not. It's the derivative with respect to the distance. So it actually turns out speed of the object increasing 9.8 meters a second during each second. That's the definition of acceleration, and hence that actually works for number one. Now we have a 500 kilogram sports car accelerating from rest, and we want to know how far it's traveled during the first 6 seconds. So to be clear, this is a distractor. We don't care how much mass the sports car has. So let's just use the formula x equals, and I'm going to do a shorthand version of this formula, x equals 1/2 at squared. So we're going to have 1/2 times, now we don't have the acceleration, but we know the times 6. Let's get the acceleration really quickly. We'll use v equals at plus v naught, but v naught 0, so 30 equals equals a times 6. Got a little ahead of myself there, didn't I? And so that's going to give us an acceleration of 5 meters per second squared. And so that will go right here. And that'll give us a distance of 90 meters traveled. So I did this first, and then I did this second. All right. So this is an interesting one because it's actually pure vector summation. So what we're seeing is this. A stationary observer sees a package falling with a speed v at an angle v1 relative to the vertical. So here's the vertical, and we see this thing falling at a speed v1 like that, right? Now, a pilot flying horizontally sees the package falling vertically at a speed v2. Okay? So let's be clear. What that means is that the horizontal speed of the pilot has to be that vector right there. And it turns out that these form a nice little right triangle. Now, we don't need to do anything as drastic as SOHCAHTOA. Instead, what we can do is we can treat VP and V2 as vector components, where VP is the speed of the pilot. So I can simply say that VP squared plus V2 squared equals V1 squared. And of course, when we isolate VP, that's going to give us VP equals V1 squared minus V2 squared under a square root, which is how I'm getting choice D. Awesome. Now, here, a ball initially moves horizontally with a velocity v initial. It is then struck by a stick. After leaving stick, the ball moves vertically with a velocity vf, smaller magnitude vi. We want to know the direction of the average force. This is really a change in momentum problem, so what we want is the direction of the impulse. Again, when I said you have spheres and you have arrows, the idea here is, so part of this force, I need to stop the ball horizontally. So I need to do two things. First, I need to stop horizontally. So I need to stop in the x direction. And then what I need to do is I need to accelerate in the y direction. So I need a force that can do both of those things. So that is going to rule out quite a few of these. The other thing is that I need to accelerate in the y, but I can't have it be so gigantic that it's bigger in magnitude than this v initial. So A stops me in the horizontal, but it gives me no vertical. C puts me vertical, but it doesn't stop my horizontal. E actually reinforces my horizontal motion. So what I'm left with is a vector, either B or D. I'm going to go with B because D gives me too much vertical force. So that's how I'm getting B for number 4. All right, number 5. Oh, the standard thing. You know, I'm just going to circle C first and then read the problem. So F1 is the magnitude of the force exerted by the Earth on a satellite. F2 is the magnitude of the force exerted by the satellite on the Earth. F1 is equal to F2. This is a classic third law question. When you have, what we're basically saying is this. A pushes B, and we want to know what B pushes A with. Well, by Newton's third law, these are equal and opposite. That's really all I'm doing there. All right. Now, for the next question, a ball is thrown upwards at a height of 10 meters. It has 50 joules. And it's moving upward with a kinetic energy of 50 joules. So this is kind of a no-brainer. I know that mgh is 50, right? So I have a total of 100 joules. So here's the deal. I don't need to do all this elaborate math. I know mgh is 50, and now I go to 100. So mg times h nu equals 100, right? Well, what I realize here is, wait, 100 is 2 times 50. So that means h nu is going to be, so h nu is going to be 2 times h old. Since h old was 10, that's going to give me a height of 20. Okay. Another way to do this is I could say 50, so I could just say 50 plus 50 equals mgh nu. And I could be clear on the fact that mgh old is 50. So I have mgh old plus mgh old equals mgh nu, and cancel that way. There's a lot of ways to do this problem, but the height's 20. Okay. Now we're going to skip 7 and 8. We'll do that when we get back from Thanksgiving. Here. I want to simplify a couple things. First, I want to be clear that the weight here on the left is 9 newtons. I'm getting that by taking 0.9 times g, which is 10. Similarly, the weight on the right is 6 newtons. To be clear, I'm taking 0.6 times 10. Now let's go ahead and set up our equation to get the acceleration. So these things are attached. So I have, let's assume that it moves in this counterclockwise direction, and we'll call that positive. So I'm going to have 9 newtons, which I get from here. So I'll just say WL minus T equals 0.9 times A. And on the other side, I'm going to have, and I'll actually write that out as 9 minus T equals 0.9A. I'm going to use similar logic here to do the right one, but let's remember that we're reversing direction, so it's tension that comes first, like we did in the last. Well, like we solved this problem in class, so I'm not going to review it as thoroughly. So t minus 6 equals 0.6a. Now, what I'm going to do here is I'm going to combine these two equations. When I do that, I'm actually going to end up getting 3 equals 1.5a, and that gives me an acceleration of 2 meters per second squared. Awesome. Now let's take a look at number 10. Number 10, once again, there's two formulas for power. This formula, whenever you have a force, I want you to remember that power is force times velocity. Okay, that's in the AP, and we use that here. I might give you this on the exam since we haven't used it too often, and that really makes this easy. So 4 equals F times 2. And so F is going to end up being just a simple 2 Newton force. Okay. Now for number 11. Okay, this one's another one where we need to worry about vector sum. So let's be clear. I need the final momentum of my system to equal the initial, so it needs to balance out to 10. So what does that mean? Well, I need something that can cancel the vertical. So let's be clear. I need to cancel the vertical component. Why do I need to cancel the y component? I never had a y component to begin with. So if this has a positive y component here, then y, capital Y, needs to have a corresponding negative vertical component in order to cancel. So let's think about what that means. That rules out A and B. Now let's be clear. I have this vertical component here, which is 6 sine of 53. Okay, there's no way that 4 sine of 37 can cancel that. So this is too small. Now we've got these two. Either seems plausible. Let's just double check. So here I have 8 sine of 53. Which is way bigger than 6 sine of 37. 6 sine of 53, sorry. So that's going to rule out choice E, so that only leaves us choice D as the thing that could possibly cancel. So what I'll say here is this doesn't work because it's too big. And again, I want to be clear. I determined by seeing if vertical components balance. And that's the idea. All right. We can skip 12 and 13 for now. We're going to come back to those after break. And then for number 14, okay, power is work over time, and in this case that's going to be oh, look at this little distractor. The work here is going to be mgh. They distracted me with the time, so this is a distractor, so we don't even need that, so I'm going to get rid of it. Alright, now we'll skip 15. We're not going to do that until later. All right, now, number 16. Working on number 16, let's keep this simple. So I have mass and little mass. And here's the thing. We want to conserve momentum. Excuse me. Love this air quality. Now, I'm saying I'm moving M and V up, and I'm attached to the balloon, so the balloon is going to want to move downwards. Well, that means it's going to have a small v so that these two momentum can be equal, because this will be a negative momentum, and this will be a positive momentum. So just to be clear, the initial momentum is 0. I have little m moving at a big V, plus I have the balloon moving at its final V. When I isolate V final for the balloon, I'm going to get that v final equals little m over big M times the velocity of the balloon. Since little m's smaller than big M, Vf has to be less than V initial. So it's going to move down with a speed less than V. All right. Check this out for number 17. We know the force and we know the time, which is the impulse. And another term for impulse is change in momentum. They love doing this all the time. Like, you'd think they'd be sick of it, but every single time they're going to mix up the terms change in momentum and impulse. All right. Now here. 18 we could technically do, but I want to move into that when we do E&M next semester. 20 we don't need. Now here, a classic conservation of momentum. We have mv0, and what happens? It explodes into two pieces. One piece has a mass of 2/5 m, and it moves at a speed negative v0 over 2. Why do I say negative? Because it's moving to the left, so I'm going to make that negative. Plus 3/5 m times v final to the right that we're going to solve for. So let's isolate a couple things. When I bring this to the other side, I'm going to get mv0 equals negative mv0 over 5 plus 3/5 mv final. That's going to give me 6/5 mv0 equals 3/5 mv final. I can cancel the 5s, the m's. I divide, and I end up getting that v final is simply 2 v0. Excellent. We're going to actually skip all the problems on this page. We'll be able to do this more effectively after break. I could have you do them, but they're not quite what we've covered here. This is a cute question. So let's talk about height and projectiles. So normally, maximum height is going to be v squared over 2g is equal to h. How did I get that? Just remember v squared equals 2g times x minus x naught. I'm going to just call this whole thing height because that's h minus 0. So I'm getting v squared over 2g equals h. Now let's talk about for the projectile, we're going to get v naught squared sine squared theta over 2g is the height of the projectile. Now we're at 45 degrees, right? So let's be clear. The sine of 45 squared is actually root 2 over 2 squared, and that's 1/2. So what we're going to end up getting is that the maximum height of the projectile is only half of the original height. 26 we skip. We're not doing torque yet until after break is what I'm trying to say. All right, this air quality is kind of getting to me. Now, for number 27, I mean, come on, no air resistance, parabolic path, the acceleration's downwards, and the net force is always downwards, okay? Because it's always caused by gravity. 29 to get the center of mass. So this is 10, this is 5. The center of mass is going to be closer to, it's just going to be B, closer to that one. We don't need to worry about 30 or 31. We will move just a little bit ahead and say this. So 32, no. 33 we could do, but I'm not going to have you do that. So here, our classic inclined plane. Let's draw our own free body diagram. We've got the normal. We've got mg sine theta, and mg cos theta. Now let's go see what they want. We want F necessary to pull the block up the plane with constant speed. So what that would mean here is that F has to equal mg sine theta. This is a 3, 4, 5 triangle. And this is theta. So that means F is going to be 5 times 10, which is 50. The sine of theta is going to be 3 over 5, and that's how I'm going to get a 30 Newton force. 35 will skip, so that pretty much wraps up our solution set to these problems.